Welcome everyone, and thank you for joining us today. I'm excited to introduce our AI terminology training session. On this first slide, we see some key terms that we'll be exploring throughout the presentation. We'll cover concepts like tokens, agents, RAG, APIs, LLMs, and AI itself. Our goal is to make these terms clear, practical, and easy to understand, so you can communicate confidently about AI. Let's get started and dive into these foundational concepts together. Let's start by talking about the importance of having a clear glossary. When we use consistent and understandable terms, it really helps reduce confusion across a variety of tasks, whether it's prompts, automation, reporting, content creation, or digital workflows. Clear terminology makes everything smoother and more efficient. Now, practical use is a key point here. When people understand the terms involved, they can compare tools, features, risks, and benefits more accurately. This understanding enables better decision-making and helps prevent misunderstandings that could lead to mistakes or missed opportunities. Moving on to decision-making, knowing the jargon is crucial. When you understand the language around AI, you're better equipped to ask insightful questions, participate meaningfully in discussions, and use AI tools correctly. It's about empowering yourself to make smarter choices. And let's not forget confidence. When technical terms are explained in plain language and connected to real-work situations, participants learn faster. They feel more comfortable applying what they've learned because it feels relevant and accessible. Finally, understanding starts with a simple idea. Always start with the reason behind the term before teaching the words themselves. When you grasp the purpose or the problem it addresses, the terminology becomes much easier to learn and remember. So why does AI terminology matter? It's about clarity, efficiency, and empowerment. As Bernardo D. Frayne emphasizes, effective AI terminology training ensures everyone is on the same page, which is essential for success in this fast-evolving field. Let's start by looking at some of the core terms in AI. First, we have generative AI or Gen AI. This is a type of AI that creates new content, things like text, images, audio, code, and even videos, based on prompts or examples that we give it. It's really about AI that can produce original material, which is a pretty exciting development. Next, we have deep learning, often abbreviated as DL. Deep learning is a specific kind of machine learning that uses layered neural networks. These networks help handle complex tasks such as recognizing images, understanding speech, or processing natural language. It's what powers many advanced AI capabilities today. Then there's machine learning, or ML. This is a broader category where systems learn patterns from data rather than being explicitly programmed for every single rule. So instead of coding every step, we feed data into the system, and it learns how to make predictions or decisions on its own. Finally, we come to artificial intelligence itself. AI is the overarching field focused on making machines perform tasks that typically require human intelligence, things like reasoning, problem-solving, understanding language, and more. These four terms, AI, ML, DL, and Gen AI, are the most common starting points when exploring the field. They form the foundational concepts that help us understand how these technologies develop and connect to each other. They're essential for grasping the overall theme of AI's rapid evolution and expanding capabilities. Now, let's talk about some key terms you'll often hear in this field. First up is NLG, or natural language generation. This is the part of AI that actually produces readable responses, summaries, emails, reports, or even scripts. Think of it as the AI's way of crafting human-like language from data. Next is NLU, which stands for Natural Language Understanding. This is what helps a system grasp the intent behind a message, as well as its meaning and context. It's like the system's comprehension skill, enabling it to interpret what you really want or mean. Then we have NLP, or Natural Language Processing. This is the broader field that focuses on helping computers work with human language, whether that's understanding, generating, or analyzing text. Another important term is LLM, or Large Language Model. These are massive models trained on huge amounts of text data, allowing them to understand and generate language with impressive sophistication. You'll find these terms frequently used when discussing chatbots, writing tools, or any AI that interacts with language. Together, LLM, NLP, NLU, and NLG form the foundational language terms that underpin much of today's AI communication technology. Understanding these will help you grasp how these systems work and improve their application. Now, let's take a closer look at some of the key terms we use when working with AI models like ChatGPT. First up is token. Think of tokens as the building blocks of the text. It's the amount of text, instructions, and conversations that the model can consider at one time. This directly impacts the model's limits, how fast it can respond, and the overall cost of processing. Next is the context window. This is essentially the space the AI uses to keep track of everything within a session. It includes the instructions or background information guiding the conversation, often called a hidden or primary instruction. This helps the AI understand its role, boundaries, and how it should behave throughout the interaction. Then we have the system prompt. This is the specific instruction or question we give to the AI at the start. It sets the stage for what we want the model to do or focus on. Finally, prompt is a broader term that refers to any input we provide, whether it's a question, a command, or a set of instructions. These terms, token, context window, system prompt, and prompt, are especially important when you're working with tools like ChatGPT, Claude, Gemini, or similar AI systems. Understanding these concepts helps us craft better interactions and get more accurate, efficient results. Let's take a closer look at some key terms in the AI model workflow. First, retrieval-augmented generation, or RAG for short, is a method where the AI first searches trusted sources of information before generating an answer. This helps ensure that the responses are accurate and reliable. Next, we have fine-tuning, which involves additional training on specific data to make a model better suited for a particular task, tone, or domain. This customization makes the AI more effective in specialized areas. Then, there's inference, the stage where the trained model is actually used to answer questions, classify data, make predictions, or generate content. It's the application phase. And finally, training is the process where the model learns patterns from large amounts of data, building the foundation for everything that follows. These terms are essential for understanding how AI systems are built, refined, and ultimately used in real-world applications. Now, let's talk about the effort to make AI behavior align with human goals, instructions, and safe values. This is often called alignment, and it involves designing rules, filters, and controls that help reduce outputs that could be harmful, unsafe, or simply off-topic. The goal here is to ensure AI responds in ways that are responsible and aligned with our expectations. Next, there's the issue of bias. Sometimes, AI outputs can unfairly favor certain patterns, perspectives, or groups. This can happen because of the data it's trained on or how it's designed, leading to skewed results that aren't fair or balanced. Then we have hallucination. This is when AI gives a confident answer that's actually incorrect or even completely made up. It might sound plausible, but it's not based on real data or facts. All these terms, alignment, bias, hallucination, are key to understanding why AI answers can sometimes vary in accuracy and trustworthiness. Recognizing these issues helps us improve both the safety and reliability of AI systems, which is at the heart of our overall goal in AI development. Now, let's take a look at some key concepts that are transforming how machines understand and process data. First, we have the idea of a model that can handle multiple types of input, like text, images, audio, or video. This is what we call a multimodal model. It allows systems to analyze and interpret different kinds of data simultaneously, making them much more versatile and intelligent. Next, we move to semantic search. Unlike traditional search methods that rely solely on exact keyword matches, semantic search focuses on meaning. It understands the context and intent behind a query, so results are more relevant and aligned with what you're actually looking for. To support these advanced search capabilities, we need a specialized database known as a vector database. This type of database is designed to store embeddings, numeric representations of data that capture its meaning, and to quickly find items that are similar based on those embeddings. Speaking of embeddings, this is a crucial concept. Embeddings convert data like text or images into a numerical format that machines can easily compare. Think of it as giving meaning a numeric shape that allows for similarity comparisons across different data types. Finally, these concepts are especially useful in areas like smart search, personalized recommendations, and retrieval systems. They enable machines to understand and connect data in ways that were not possible before, making our interactions with technology much more intuitive and effective. All of these ideas, multimodal models, semantic search, vector databases, and embeddings, are interconnected. They form the backbone of modern AI-driven search and knowledge systems, and understanding them helps us unlock the full potential of intelligent data processing. Now let's take a closer look at some key automation concepts. First up is the agent. An agent is essentially a smart helper that can reason, decide on the next steps, and perform actions all toward achieving a specific goal. It's like having a digital assistant that can think through problems and act accordingly. Next, we have the workflow. Think of a workflow as a sequence of connected steps that move from a trigger, like receiving an email, to a result, such as updating a record. These workflows are often automated, making processes smoother and more efficient. Then there's the web app, which is simply a browser-based interface that people can interact with directly. It's accessible, user-friendly, and designed for real-time use. Moving on to the API, or Application Programming Interface. This is like a bridge that allows different software systems to talk to each other, sending and receiving data seamlessly. All these terms, API, web app, workflow, agent, are common in business automation and digital operations. They form the foundation for building smarter, more efficient systems. Understanding these concepts helps us see how automation can transform everyday business tasks into streamlined processes. Let's take a closer look at the different types of data and learning methods we use in AI. First, we have datasets, which are essentially collections of examples, records, or files that are used for training, testing, or evaluating our models. These datasets are the foundation of machine learning, because they provide the information the model needs to learn from. Moving on, there's reinforcement learning. In this approach, the model learns by trial and error. It receives rewards or penalties based on its actions, which helps it understand which behaviors lead to success and which to avoid. It's a bit like training a pet, where positive reinforcement encourages good behavior. Then we have unsupervised learning. This is where the model finds patterns or clusters in unlabeled data, meaning the data doesn't come with predefined answers. The model explores the data on its own, discovering structures and relationships that might not be immediately obvious. Next is supervised learning. Here, the model learns from labeled examples, so input data paired with the correct answers. This approach is very common because it provides clear guidance, making it easier for the model to learn accurate mappings from inputs to outputs. All these methods are foundational approaches in machine learning. They help us understand how AI systems learn from data, whether through trial and error, pattern discovery, or guided instruction. Recognizing these different learning types is key to understanding how AI models are built and improved over time. Now, let's talk about stored learned values, which are the core of how models make predictions or generate outputs. These are called model weights, and they represent the internal values a model learns during training. Think of them as the model's memory of what it has learned so far. Generally, more parameters, meaning more weights, can give a model greater capacity to learn complex patterns. But it's important to remember, more isn't always better. Sometimes, having too many parameters can lead to overfitting or increased complexity without improved results. Next, I want to highlight the concept of parameters, which are essentially the individual components that make up these weights. They're like the dials and switches the model adjusts during training to improve its performance. Moving on, we have proprietary models. These are closed systems, meaning the company owns and controls everything about them. They're not openly shared with the public, which can impact how flexible or transparent you can be with their use. In contrast, open source models are different. Their code or weights are openly available under a license, so anyone can examine, modify, and use them. This openness fosters collaboration and innovation in the AI community. Finally, understanding the ownership and access terms of models is crucial, especially when evaluating different platforms. These terms influence cost, flexibility, and how you can use the technology. Always consider these factors carefully to choose the right solution for your needs. And that wraps up this overview of model weights, parameters, and the importance of understanding ownership and access terms in AI. Let's talk about some key terms that help us understand the performance of AI systems. First, we have compute, which refers to the processing power used to train or run AI models. This is often linked to how fast the system can operate and how much it costs to do so. Next is scalability, which describes how well a system can keep performing as the number of users, tasks, or data increases. Essentially, it's about whether the system can grow efficiently. Then there's throughput, which measures how much work a system can handle over a period of time, like requests per minute. This gives us an idea of the system's capacity. Finally, latency is about how long it takes to get a response after sending a request, so the delay before you receive an answer. These terms, latency, throughput, and compute, are crucial because they help us understand the speed, capacity, and operating costs of AI systems. They all connect back to the overall theme of designing efficient, effective AI solutions that meet performance expectations. Let's look at some effective ways to reinforce learning. First, I ask learners to repeat the meaning in their own words or to apply it to a task. This helps ensure they truly understand the concept. Next, we check understanding by encouraging questions or quick summaries. Moving on, I explain how AI differs from machine learning and how NLP differs from large language models. Clarifying these distinctions is key. I also compare similar terms to highlight subtle differences, making the concepts clearer. To make it more relatable, I use a short, practical example, something simple that helps learners grasp the idea faster than a lengthy explanation. I connect these terms to real-world tools like ChatGPT, Zapier, or Canva, so learners see how these concepts appear in daily use. When introducing abbreviations, I start with the full form first, then explain what each word means to avoid confusion. Finally, I introduce new terms in plain, everyday language before diving into technical labels, making the learning process smoother. Using this step-by-step sequence helps make complex AI vocabulary easier to remember and understand. Let's dive into some training tips to help learners remember these key AI terms more effectively. One of the best ways is to link each term to a task, a tool, or a real-world example. For instance, when we talk about a confident but wrong output, think of it as an AI confidently making a mistake, which highlights the importance of understanding the context and checks. Next, hallucination in AI refers to when the system generates information that isn't accurate or real, something to watch out for. Meaning in numbers is about how AI interprets data quantitatively, turning numbers into insights. Embedding is a way AI converts words into mathematical representations that it can understand, which is crucial for many language tasks. When we say AI that acts, we're talking about systems that can perform actions based on data, like virtual assistants. An agent is an AI that can make decisions and act independently in specific environments. Software-to-software connection and API are about how different programs communicate seamlessly. Think of APIs as the bridge that allows different tools to work together. Search plus generate combines looking up information and creating new content, which is fundamental in generative AI. RAG, or retrieval augmented generation, is a technique where AI pulls in external data to produce more accurate outputs. A small text unit, or token, is just a piece of text that the AI processes, often a word or part of a word. Instruction to the AI, or a prompt, is what guides the system to produce the desired response. The large language model, or LLM, is the backbone of many AI applications, capable of understanding and generating human-like text. Creates new content refers to Gen AI, which generates text, images, or other media. Layered ML networks, or deep learning, involve multiple layers processing data to recognize patterns. Learning from data is the core of machine learning, enabling AI to improve over time. Finally, smart systems and AI are about how these technologies are integrated into our daily lives, making tasks easier and more efficient. Remember, this cheat sheet is a quick reference to help you grasp these essential concepts and see how they fit into the bigger picture of AI training. Now, let's look at some key evaluation metrics and concepts that help us understand and improve AI models. First, we have precision, which tells us, out of all the positive predictions our model makes, how many are actually correct. It's about accuracy in positive predictions. Then, recall measures how many of the actual positives our model successfully identifies, so it reflects the model's ability to find all relevant cases. The F1 score combines these two, providing a balanced measure that accounts for both precision and recall, especially useful when we need to balance false positives and false negatives. Moving on, the loss function is a crucial concept. It quantifies how wrong our model is. The goal is to minimize this to improve accuracy. Overfitting is when a model memorizes training data instead of learning general patterns, which hurts its performance on new data. Underfitting, conversely, happens when the model fails to learn enough from the data, leading to poor predictions. Bias refers to systematic unfairness in a model's predictions, which can have serious ethical implications. Explainability, or XAI, is about making AI decisions transparent and understandable, important for trust and accountability. Alignment ensures that AI behaves in ways consistent with human values and expectations. Data privacy focuses on safeguarding user information, protecting sensitive data from misuse. Robustness is the model's ability to handle unexpected or noisy inputs without failing. Fine-tuning involves adapting a pre-trained model to specific tasks, saving time and resources. Transfer learning allows us to reuse knowledge from one task to accelerate learning in another. Multimodal AI models handle multiple data types simultaneously, like text, images, and audio, which makes them versatile. Generative AI creates new content, such as text, images, or videos, opening up creative possibilities. Diffusion models, for example, are used for high-quality image generation, like creating art with tools such as Stable Diffusion. An epoch represents one complete pass through the entire dataset during training. A batch is a smaller subset of data processed at once, which helps optimize training efficiency. Gradient descent is the method we use to minimize errors by adjusting the model's parameters, and backpropagation is how we propagate the error backwards through the network to update weights. The learning rate determines how quickly our model updates during training. If it's too high, training becomes unstable. If it's too low, learning is slow. The model itself is the trained system that makes predictions based on learned patterns. Parameters are the internal values the model learns during training, shaping its behavior. Weights and biases are the core components within neural networks that influence the output. Transformers are a modern architecture, powering models like ChatGPT, allowing us to handle complex language tasks effectively. Layers are the building blocks of neural networks, stacking to learn hierarchical features. Embeddings are numerical representations of data, like converting words into vectors, making it easier for models to process and understand complex information. A dataset is simply a collection of data points used to train and test the model. Training is the process of teaching the model by exposing it to this data. Inference is when we use our trained model to make predictions on new, unseen data. Labels are the correct answers we provide during supervised learning, guiding the model's training. Features are the input variables that the model uses to make predictions, such as age, temperature, or text. Finally, data augmentation involves artificially expanding our dataset, like flipping images or adding noise, which helps our model generalize better and improves performance, especially when data is limited. Let's take a moment to review some key terms we've discussed today. First, a model is a trained system that we use to make decisions or predictions. Think of it as the core of AI that learns from data. An algorithm, on the other hand, is a finite sequence of instructions that a computer follows to perform a task, essentially the recipe for training or running a model. Parameters are internal variables that the model learns during training. These are what allow the model to adapt and improve its performance. Weights and biases are specific components that adjust how the model learns, acting as the knobs and dials that fine-tune its behavior. When we talk about neural networks, we're referring to systems inspired by the human brain, capable of recognizing patterns and making complex decisions. Modern architectures like transformers have revolutionized AI by enabling more sophisticated understanding and generation of language, images, and more. Embedding is a technique where data, such as words, are converted into numerical vectors. This makes it easier for models to process and analyze unstructured data. For example, in AI systems like AlphaGo, which plays the game of Go at a superhuman level, these concepts come together in powerful ways. Artificial General Intelligence, or AGI, refers to AI that surpasses human intelligence across a wide range of tasks. It's the ultimate goal for many researchers. And finally, JSON, or JavaScript Object Notation, is a simple, text-based format used for storing and transmitting data. It's fundamental for how systems communicate over the web. Altogether, these concepts form the building blocks of modern AI, connecting how systems learn, adapt, and operate in real-world applications.